All right, welcome to our first video on financial models. And let me tell you, this lesson is money. I'm going to tell you that. So A equals P times 1 plus R over N raised to the NT. All right, so what does that mean? Well, we got to break down what this formula will do for us. But first, let's talk about what these letters stand for, okay? A is going to stand for the accumulated amount. We don't have these just filled out for you because we think it's kind of important to talk through them and make sure you understand it. The accumulated amount, the total amount after an investment, all right? And then P stands for principal, all right? That is the big word in math is initial, so the initial amount. And obviously, both of these, we are talking about money here, okay? Now, R stands for the annual interest rate. And that's important that you understand it's the annual rate, okay? And that's often given to you as a percentage in a problem, all right? N, that stands for the number of times per year that you're compounding your interest. And we will talk about that in just a second, okay? But that word is compounding there, okay? And then T is obviously time, but just understand this context, this formula, writing at the same time as talking, it's tough for me. Time of investment is always in years, okay? So if they said 6 months, you'd put 0.5 for that one. Okay, so first of all, what does compounding interest mean? Basically, it's kind of like a way of how you're making money off of your money. So let's say you had an investment for 1 year. At the end of the year, you then earned interest on that investment, okay? Well, you have an interest rate, let's say it's 5%, and you earn interest of 5%. You make that money, you put it back in the bank, and then you have more money to make next year. Here's the deal. Sometimes you will talk about, or you will in these, when you actually earn the interest. If you earn the interest annually, that's just once a year, right? Semi-annually would be twice a year, quarterlies 4 times a year, monthlies 12 times a year, weeklies 52 times a year, and daily we actually use the number of 365. Now these are going to be, I'm going to put over here, all of your different N values in the problem, okay? Now, if right now you're thinking, oh, well, if I earn money every month, right now, well, that's going to be better than doing it one time a year. Here's what you need to be careful of. And this is what I would say a lot of people don't understand about these. When you earn 5% interest after 1 month, you don't actually earn 5% interest. You're earning 0.05 divided by 12. You're earning 1/12 of the annual amount. So it's not like 5% every month, right? So be careful of that. There's a difference between annual interest rate and the number of times you're compounding. And the formula takes that into account. So let's read through this problem here. Determine how long it would take to double an investment that has interest compounded semi-annually and an interest rate of 3%. Okay, so immediately when you see that it's semi-annually, you know that N is going to be 2, and we're going to use this formula here. All right, so annual interest rate, so our R value is going to be 0.03. We got all that coming out of that, which is good. But now they're saying how long to double an investment. You can pick any amount you want. For sake of argument, let's say $10. You put $10 in, okay? So if we're going to use this formula, A equals P times 1 plus R over N raised to the N times T, watch how this works out. If I'm going to put in $10, that's the principal. I'm going to put in $10. Well, that means at the end of it, if I double it, I'll get out $20, right? And that's what doubling means. So 1 plus R, 0.03 over N. We said that was 2, right? Semi-annually. We're going to raise it to the 2t power. Why is it 2t? Again, N is 2. T is what we're looking for. Now, I skipped this one here because it's a pretty straightforward example, okay, of how we just plug in and solve for a variable, okay? But this one is going to use the logarithms process that we have been working on, and that's why we have these in here, because it's an unknown exponent. This other one doesn't have an unknown exponent. This has an unknown exponent. Okay, so right now what we want to do is we want to say, all right, well, to get this solved for that, we got to get rid of the 10. So we would divide by 10 to both sides, and we would get 2 equals 1 plus 0.03 over 2 to the 2t. Okay, now I picked 10. If I would have picked 100, that would have been 200. 5, that would have picked 10. So truly, when you're doubling or let's say tripling an investment, you can just start right at this phase because that's always going to happen when you divide both sides there. Okay, but here we are now, and we need to get this out of the numerator. I'm sorry, of the exponent. So what we do is we take the log of both sides. You can pick any base, but we take the log of both sides. Okay, so this will be the natural log of 2 equals the natural log of this whole thing. But remember, we have that property where we can bring the exponent out front. So it turns into this. And now what is that? That is literally just a number. That's a number right here. Natural log of this is a number, and then there's a 2 there. So watch this. If I divide this whole side by 2 times the natural log of 1 plus 0.03 over 2, this will cancel, this will cancel, this will cancel. And if I do that to this side, I'm running out of room here, but let's see, natural log of, hopefully you understand what I'm writing, plus 0.03 over 2. When we calculate this right here, and we would definitely use a calculator on that, that comes out to time of approximately 23.278. And that would be years. So it's going to take us around 23 years to double that investment. Okay, so now there's a second one here that we're going to talk about with money, and that's about compounding continuously. Now, it's really tricky because, again, in this format, we're only able to get into so much depth over a video or else they become too long. But this one here, and I'll talk more about it in class, about how it's important. And you honestly might not really understand it until you move on into science classes and more in-depth science classes and calculus, but it has base E, okay? And this is talked about compounding continuously, like the word sounds like. So basically, as we increase n, and that's how we would show this, as we increase n here and increase n here, what essentially happens is we approach, or we use this formula to talk about how that n value keeps getting bigger and bigger, 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 bigger. So like up here, sorry, that's off the screen. But as we kept getting the n value bigger, and then what if we went 1,000? What if we went every 20 seconds? What if we went, that would be using this formula, okay? So APERT, we use APERT. Okay, so find the number of years it will take to triple an investment that has interest. There it is. As soon as you see continuously, you're going to be using this formula right there, okay? So find the number of years it will take. So once again, we're tripling. So we are going to do this right off the bat. I'm just going to say 3, and I'm going to say 1. 3, 1. E raised to 0.045, unknown time t here. Okay, so what do? Natural log of both sides. Natural log of 3 equals 0.045 t times the natural log of e. All right, now this is the first time we have seen this, but I want you to know that the natural log of e is literally 1. And if you're like, say, what? How is the natural log of e just 1? It is, it's just 1. I mean, look off to the side here. If I asked you, what's log base e of e? What's that equal to? I hope you would say that it's 1, right? So that's just 1, and that's why one nice reason I used the natural log of both sides, when you could have used any log. But now we divide by just 0.045. So this is actually an exact answer right here. This is the amount of time and the exact answer. If you were to go crank that out, you would see that it comes out to 24.413 years, okay? Or 414 years would have been fine there too. Okay, so now the next part of this is very, very similar, okay? You need to see this is similar, and I jumped ahead with filling it in for you, but this is going to be the same concept as really APERT, but with population growth. So remember, the A stands for not the growth of the population, but the total population afterwards, all right? This A sub 0 here is the initial population. E is not a variable, remember, and then K times T. Well, K is the rate of growth. If it's growing, K will be positive. If it's decaying, it'll be negative. So same formula. It's just a matter of whether you are growing or decaying that makes the K value positive or negative. T again is time, but it doesn't have to be in years here, and often won't. All right, so the number of bacteria present in a culture at time t, in hours, there you go, obeys the law of uninhibited exponential growth. What we mean is it uses this formula. So initially, there are 100 bacteria present. So we know that. If there are 350 bacteria present at time equals 5, how many bacteria will be present at time t equals 9? Okay, well, first off, what they did not give you in this problem is the growth rate. So that's where we got to start this problem and then answer the question afterwards. So they did say there's 350. So that's going to be the A value we use. So there's 350 when the initial population was 100. E raised to the don't know what K is, but we do know that that was at time 5 hours, right? So we know this information and we can calculate the rate of, which is obviously growth here because it's bacteria and it's growing. Now, please note that we still divide both sides by 100, just like before, right? When we did these problems. So we have 3.5 equals what? Not K times 5, we have E to the 5K, right? So then we have natural log of 3.5 equals 5K times the natural log of E, all right? And then once again, boom, this is 1. So all we have left is a 5K, all right? Still way too long for me to run, but, oh man, it's bad. All right, divide both sides by 5. And now we have K. Now, please understand, if we were to crank this out, and I think I have that on my paper. I don't. I thought I did. But this will give you the K value. Okay, so I'm just going to say right now, on calc. So we definitely would expect you to be able to use a calc on this one. Okay, but you know that right now, if we go answer the question t equals 9, we have enough information because we have the K value right there on our calc. So if we want to know, all right, A equals still 100 at the initial time, right? E raised to the K times, and now we put a 9 up here. Okay, what I need you to know right now is that you can put all of this on your calculator perfectly because K is right here, all right? So you would just put that value in for K. Can you nod? Do you understand? Okay, I have no idea if you're nodding, but this is all just a number. I'm just not going to rewrite that. And I'm not going to use a rounded value. Please don't use a rounded value up here. That's silly. You don't need to. You have the exact value on your calculator. So if you do this, you do get an answer. Plug it into your calculator. Make sure you know how to do that of 953.503 bacteria at the end of this. All right. Okay, moving along here. The next concepts on here are, actually, I'm going to jump down to radioactive decay because that kind of follows this here. This follows this concept more so than the carbon dating. We'll do carbon dating last on here. So radioactive decay, potassium decays exponentially with the decay constant. Okay, so they gave you the decay constant, and they're asking what's the half-life. Half-life is, if it was at 50 grams, how long will it take to get to half of that, which would be 25 grams. So basically, and I'll play that out. I'll just play out exactly what I said. If I have this. Do you agree with me that that is an initial of 50 and after of 25? Doesn't matter if you pick 50 and 25 or 10 and 5. It doesn't matter as long as this is half. So when you do half-life problems, essentially you should start when you get the hang of it at 0.5. E raised to the negative 0.00041. Now, why did I use negative? Again, it's a decay problem. The K value is going to be negative. So then we do the natural log of 0.5 equals negative 0.00041 t times the natural log of E, which we know is 1. So then when we divide both sides by negative 0.00041, we are going to get time. It does come out on there as approximately 1690.602 years. I'm taking that straight from my notes. Obviously, I'm not taking the time to put that all in my calculator, but that's how you would do that one. Okay, same logic with, actually that's a good progression. We did that one first. With carbon dating is they tell you that carbon-14 has a half-life of 5,600 years. So if you're going to use carbon dating, a fossilized leaf contains 70% of its normal carbon. How old is it? Well, if you know the half-life, then you can figure out the decay rate on that problem. So just start with anything. So here's 0.5 equals e to the 5600 k, because the rate times the years, half-life, that's how we get that. So then we do the natural log of 0.5 equals 5600 k times the natural log of e, divide by 5600, and you get the k value. That is that. Okay. Now, I'm going to say that because I'm not going to round it right now. I'm just going to use it in the problem. Now, again, the question is asking, well, the fossilized leaf contains 70% of its normal carbon. So if it hasn't gotten down to 50%, it's going to be a time less than 5,600 years using this process. So what we're going to do is do the 0.7 here. So 0.7 is equal to e to the k times t. But remember, when we do this, this is not unknown right now because the rate is the same no matter what the percentage is, right? So 0.7, so we'd have natural log of 0.7 equals k times t times the natural log of e, gone. So you're going to divide by k. K is not, I just keep saying that, it's not a variable, it's a number that you already found in your calculator. And then that would come out to 2,881.609 years.